So a norm is a function that tells how big a vector is. So magnitude or absolute value, something along those lines. So more precisely, a norm is a functional defined on the vector space and having non-negative real outputs, which satisfies the following properties. So it needs to be positive in the sense that it can only take non-negative values. It needs to be definite in the sense that the only thing with magnitude 0 is the 0 vector itself. It needs to satisfy absolute homogeneity, meaning that you can pull a scalar multiple out as long as it comes with absolute values. And it satisfies the triangle inequality, which says that the magnitude of a sum is less than or equal to the sum of the magnitudes, not necessarily equal to. Now, because of the fact that we've got an absolute values coming out here, and because of the fact that we've got an inequality right here, this is not a linear functional. All right. And I should also point out here that this positivity property is just a recapitulation of this property right here. So it's a little bit redundant to say it since I already put it up above, but what the heck, just be on the safe side. Okay, so now the way this goes is that if V is an inner product space, then we can define a norm by taking the square root of the inner product of a vector with itself. So that will be our definition, our standard definition of what a norm is on an inner product space. So this always defines a norm. However, you can't go backwards. It's not true the other way around. So in other words, not every norm comes from an inner product. And so there's lots of good examples of norms that don't come from inner products. So for example, if we take our vector space to be Fn, then let's see, so if we had picked some number p, and it should be finite, but it can be 1 or anything greater, any real number greater than or equal to 1, then the p norm of the vector v is defined by, and we'll give a little subscript p to indicate it's the p norm. It's just like a little label. So what we do is we take the sum of the coordinates and we raise each one to the pth power, and then when we're all done adding them up, we take the pth root. So for this situation, only p equals 2 is associated with an inner product. Now, any other value of p will work just fine, but yeah. Okay. Yeah, there's just no inner product, and actually you'll see this comes up in the exercises. So 6A number 18 looks at this situation. And if we take the same vector space, then the infinity norm is taken to be the maximum of the absolute values of the coordinates. And then it turns out that this is actually the limit as p tends to infinity of the p norms. Yeah, and so you can ask yourself, what does a circle look like in these different norms? Because a circle is a set of all points that are at a fixed distance from the center. So if your circle is centered at the origin, you can say a circle is going to be all points of a given fixed magnitude. Well, if we look at the 1 norm, so if we take p equals 1, then let's see, let's just draw a circle of radius 3. So I could go 1, 2, 3, right, in either direction, but I could also go over 2 and up 1. So that's going to be same distance from the origin. I could go over 2 and up, sorry, over 1 and up 2, and I can go straight up 3. So then you see that actually in this metric, a circle looks like a diamond. And you might think, what kind of crazy crackpot would ever use this as a notion of distance? Well, if you're a cabbie in Manhattan, it makes absolute perfect sense to think about distance in these terms, because you can only drive on the grid, right? And so this is sometimes called the Manhattan metric for exactly that reason. Now, if you go to the opposite extreme and you look at the infinity norm, or maybe I shouldn't say equal to, goes to, and you work it out, you'll see that the set of points that's within distance 3 of the origin actually looks like this. And if you do it for p equals 2, of course, you're going to get a circle. And that's going to show just how bad my sketches really are. Oops, okay, I shouldn't have done that. So that's p equals 2. And in general, for any value between, larger than 2, you'll have something that's kind of fatter than a circle and almost a square. And for any value that's between 1 and 2, you'll have something which is kind of like a diamond, but sort of roundy at the corners, going through like that. So those are the different geometries that you get from looking at different norms. Closely related to, sort of closely related to the idea of a norm is the notion of a metric. So a metric is a function that tells you how far apart 2 points are. So a metric on a set X is a function D, takes 2 arguments, 2 points, and it spits out a positive or a non-negative real number, and that's interpreted as telling you how far apart they are. And so in order for this to make sense as a notion of distance, it needs to satisfy a couple properties, namely the distance from a point to itself has to be equal to 0. The distance from x to y has to equal the distance from y to x. So no one-way streets allowed. And the last one, which is the distance from x to z, is less than or equal to the distance from x to y plus the distance from y to z. And so this is like the triangle inequality for the metric here. It's just saying that if you're going to go from x to z, you can't get there quicker by first going to some intermediate point y. Doesn't work. Okay, so that's the triangle inequality for the metric. And now maybe that makes a bit more sense why it's called the triangle inequality. Now, notice here that I said this is for a set. It doesn't necessarily need to be a vector space. It can be defined much more generally than that. And there's lots of good reasons why you might want to do that as well. Now, if your set is a vector space and it has a norm, then you can always define a notion of distance in terms of that norm, like I said, by looking at the difference. So in this definition, this part in here, being able to take the difference, that requires that you have a vector space. And then, of course, the norm requires that you have a norm. Yeah, well, duh. Okay, so just a quick recap. The way it goes, in order of like sort of most fancy to least fancy or most basic, it goes something like this. If you have an inner product, so this means you have notions of things like angle and orthogonality. From that, you can get a norm. You can define a norm, and then that gives you a notion of size. And then from that, you can get a metric. And with a metric, you have a notion of distance. So inner products are great because they give you all this stuff. And there's math classes that concentrate specifically on this place or this place or this place. If you take a topology class, you'll look at metric spaces, which are these real primitive things here. And you actually might look at topological spaces, which are not metric spaces, and they're even more abstract and weird. But then with a norm, you've got a bit more structure because you know what the size of a point is. And then with an inner product, then you can really do all kinds of interesting geometry.